Hey, Pedro.
Hi, James.
You think I should create a breakout room?
Nah, only only 5 people.
If that.
Hmm?
Well, it's just if one person needs help on their own.
Oh, but for the paper, I think we should be all helping each other out,
That's
and
good.
we
I'll
could.
create I'll create some
Okay.
just so can't doesn't do any harm. I hope people join us. I emailed the link just now. Hey, Dylan.
Hey James, how you doing?
So,
So.
when you said you weren't feeling well, I said, okay, I probably shouldn't be coming in either. I, uh, so
Did,
thank you for inspiring me to say I was going to do this online.
did you travel last week?
Yeah, I was traveling last week and I got sick.
Yeah, I feel like every time I travel a lot, I come down with something.
I thought I'd be over it by now, though, but I'm not. And I feel a little frustrated because no, I don't enjoy, I don't enjoy being sick.
I get that.
Unless nobody does, but
Yeah.
I
Also, I
wound
didn't
up.
get a chance. Oh, I
Yeah.
was just gonna say I didn't get a chance to look at the email. You said there's some FBA stuff, whatever. So I'll
Well, yeah, I was just saying that the conference I went to was mainly an FBA conference. It was organized by Kolodenko, who's a big FBA guy who's based in University College, Dublin.
Mhm.
And unfortunately, I missed part of the conference because I got sick, but I did hear quite a bit. And something that did interest me was there was a person in Dublin, not Dublin in Ireland, but not in Dublin in Galway, um, who what's what's her name? Thiele, Thiele, and she's been doing um, some pretty large scale flux balance analysis of metabolism, sort of whole body metabolism, um, including trying to include uh, trying to include trying to include the gut microbiota.
Mhm.
So
Yeah, I
if
know
you're
my
not
professor Eugen is really interested in that and wondering if there's something we can do metabolic way with.
right, well, so that might be something to you might look her up and see if there's. No, I don't know if what she's doing is relevant to you, but you might take a look and see if there's anything she's doing that would be helpful.
Mhm.
Maybe not for your project here, but for your future work. Um, I found some of the things she was doing quite impressive.
Hmm. Okay. Yeah, I'll look her up. Do you mind what is her name one more time?
I'm trying to remember her first name now. Her last name is Thiele,
Oh.
and if you look up that name in Galway and systems biology, I suspect there aren't that many. I mean, not that many people who meet those criteria. So
Okay. Just locked my keyboard. I forget.
I like me. So I guess we're short one person. I hope he's not there in the classroom waiting. Everybody got my email, so
Yeah.
I'm sorry, but I'm not feeling well, so I thought it was probably better to do this remote today. Let me just check and then message this, and then I'll get started. I don't see any. I don't see any. Shall we just get started and hope he joins us when he can? You didn't have any trouble getting into the meeting, did you, Lakshmi?
No, it just asked me for registration and then it
Okay.
let me in.
All right. Well, welcome back. I appreciate your understanding about today. And I apologize for being a little bit congested today. I'll try not to cough too much. So I want to do two things today. I want to continue the discussion of fitting that Pedro introduced last week. And so you'll be starting using the same notebooks that you were using last week. And if you can't find them, ask in the chat and Pedro can give you links to versions of that. And then I want to do a model replication study based on that paper I asked you to read a few weeks ago. So we're going to talk about fitting. I'm going to review a few details that were in the textbook that Pedro didn't cover very briefly. The misfit exercises are in this Google Drive here. I didn't update them. They're numbered as from a year or two ago. And then we'll go in and do the fitting exercise. I would do the phase locking exercises. So before we do that, could I ask you to give me updates possibly on your projects? I'd ask you to just prepare a couple of slides for today. And if you could, I'd appreciate it if you could walk us through where you are with your projects. And I can turn the screen share over to you. Dilla, do you want to present something a little bit?
Yeah, I can do that.
Okay.
Just send a request. There we go. Okay, can you guys see that?
Yeah, it's showing in edit mode, not in present
Oh,
mode,
yeah.
although it's not a big deal.
Okay. Yeah, so I'm doing essentially like this week I've just kind of done some initial stuff with FBA, FVA, and E enzyme constrained versions of that. So I'll just kind of go through what I've done so far. Okay, this is the name of the model that I'm using. It's for E. coli, and it's the most like up-to-date full genome model we have of that. There's 1,515 genes, 2,712 reactions, and then 1,877 metabolites. And so I downloaded that one. And then there's this tool in Python called Cobra, and it just kind of does all of this FBA stuff. So the big picture is you're just solving this equation here where S is the like stoichiometry. So like this is wrong, but like 6 water plus 6 glucose goes to 12 H2. I don't know. Whatever that like equation is for all of the chemical reactions in your metabolism. The numbers in front are determined by the stoichiometry matrix. And then this VJ here is a flux. So for each metabolite or reaction, I forget which, there's a flux of metabolites through that reaction. And so you're just setting that equal to 0, which is like equilibrium, where all the reactions are in steady state. And then you can solve that relatively easily. And so for the base model, which is just doing that with the I model that I downloaded, has some like basic inputs and outputs kind of stuff. If you just load it and solve it, you end up with a growth rate of 0.8770 maybe like doubling rate or something. That's also something I forgot to mention is you're optimizing the growth rate along with this mass balance equation here. But this just like outputs, these are just some common reactions that I recorded, but it gets this for every single one. So this is saying it's taking up this much glucose, this much O2, no acetate, ATP, it's producing that much. And this is just like the kind of what you get from this analysis, and you can do this for all those 1800 or however many metabolites. And so then the next thing I did was flux variability analysis, which is kind of the same thing, but instead of optimizing for growth rate, you're loosening that like growth rate constraint a little bit. And so you have this alpha term here, which is a percentage. So you're saying like at 90% of optimal growth, what is the minimum flux that is possible through each reaction, and what is the maximum flux through each reaction. So this just kind of accounts for the fact that like we kind of make up this growth rate that we're optimizing of however many like metabolites it is. So this just gives us more of a range, which is kind of more accurate since the equation we make up is like made up or whatever. So this just gives you kind of a broader picture of what's going on. And so these are the same ones as above. You can see the minimum for glucose is uptaking 10. The maximum is uptaking 9. And so something like that you can kind of interpret from this is if it has a really small range, then it's saying that there's not a lot of like variation allowed in the system. So like it's a quasi, I don't know, you can like read this as it's an essential gene kind of, or it's just more important. If it's a wider range, then it's not quite as important. So O2, like you can do anaerobic growth in this bacteria. So like it's not required or as essential. There's other pathways it can go through. And so like FBA just gives us a way to measure like, or gives us some sort of measure of the like range that each pathway has, if there's other pathways that can kind of account for what that reaction is doing. And yeah, so I did that one. And then the other one that I have is I did an enzyme constrained FBA, which is sort of the same thing, but now we're adding another equation to that thing we're solving, which is we're just adding a constraint of like each enzyme that catalyzes these reactions isn't like infinite. It's constrained in certain ways. One of them is there's not a like infinite number of them, so that will limit the amount of reactions that like can actually go on at one time. And then also like just the kinetics of it will also like play a certain role. So those are kind of these equations, and they're just sort of incorporated into that like big matrix equation you're solving for. And just to start off with, instead of like doing the in detail stuff of like finding the proteome budget and all that sort of stuff, I just did like a simple thing of from the first thing I did, getting the max flux, I just limited it to like different numbers. So this alpha is like a percentage. So that kind of simulates like this enzyme is constrained, so it's not going to reach this like max unconstrained value. It's going to reach like 30% or 50% or something like that. And so there were different values for some of those more important ones. And this was just kind of a way to see like, okay, how does doing this affect the math of how it works out? And so here are the growth rate comparisons. of that. And then another thing is I did it under different like conditions. So when there's glucose available, glycerol available, and then just everything available. And you can see here that when you constrain some of I only did it for like important ones. But when you constrain those important enzymes, you see a big decrease in the like allowed growth rate. And so those are the percentages that we see from there. And then here's like kind of just a graph of how they all compare. And this is just comparing like the main FBA to the enzyme constrained FBA. And so this is kind of just like initial learning how these tools works, all that sort of stuff. But in order, like the idea for this project is to compare, okay, how much more accurate are these different constraint methods? There's another one I haven't done yet. But how much like more accurate are they at predicting growth? And so that will require getting actual data of like growth medium and what the actual growth rate is from actual experiments, and then seeing how well do all of these methods match up to it and how accurately do they predict it. And you can also do things like knock out certain genes. And then there's data sets for that too. And so you can compare to it. So I've just kind of done like learning the tools kind of stuff at this stage, but that'll be kind of the next steps is doing the third constraint method and then getting some actual like data to kind of match these up against so that we can like compare against real world scenarios.
Right. So this is to ask you when I saw your first or second slide. So here you're comparing the growth rate for different substrates, for different media.
Mhm.
And so then, yes, absolutely, you could say, if you knock out a particular pathway, perhaps that pathway is only important when they're consuming glycerol and not when they're consuming glucose. So that knockout, you'd see the glycerol growth rate would go down, whereas the glucose would not go down very much.
Mhm.
So
Yeah, and there is specific experiment. I think that was the like TN-seq idea is that you can get those knockouts and like match them to growth rates and stuff like that. So I might be able to do something like that for big data and see if that's something. But initially, it'll just be kind of single experiments. What does this look like? And in
But-
these different things, does it match up?
but you would expect that, I mean, for example, if you're anaerobic versus aerobic, then you'd expect different pathways to be active. So then knockouts might have very different effects on the anaerobic and aerobic growth rates with the same substrate. So even if you don't have the experimental data, you could at least do some simulated tests of that kind, and then clearly it's more interesting if you could find experimental data as well.
Yeah.
Great.
Yeah, I still need to like play with this more and get really comfortable with what are the inputs, outputs, how can I like kind of play with it. But I've just sort of been able to do exploratory learning all these kind of tools and stuff so far.
But this slide makes clear how you could use this kind of model to say something
Mhm.
meaningful.
Yeah. Yeah.
Right. All right. Anything else you want to say today or that?
I don't think so.
Okay, great. Thank you. Varalakshmi, you want to give us an update?
Yeah, sure. Mm. I'm so sorry. Okay. Last week, I have read few papers, and then I have shortlisted three major literatures which was explaining about the cell's response towards the glucose molecule. And last week, I have replicated this paper, which was, giving out the information about how each metabolites inside the cell were reacting with respect to the glucose concentrations. And also I tried to generate for different glucose concentration how a pyruvate molecule was like trying to replicate. But this model was directly available with I can download it with URL and then I can access it. So the another paper which had defined the exact mathematical model for cancer cells and how the proliferation of the cancer cells with respect to aerobic metabolism and anaerobic metabolism using glucose and lactate. So this is also a paper like which we discussed when we met during our initial meet while discussing about the project. So what I did was this time there is no direct model available for this particular paper. So I tried to build this model with antimony. So if you can see my code. So I just so in the paper they have explained these scenarios with multiple cancer cell lines like cervical cancer, colon cancer, and glioblastoma. So what I tried to do is I tried to take one particular condition of parameters. So I took glioblastoma and I try to analyze every parameters that is been given in the mathematical cell. So for example, so what is the proliferation tau? What are all the parameters that they are considering that for? And they have a toggle switch between glycolytic and oxidative because this is exactly not a cell that they have considered the equivalent cancer phenotypical cells. So they have a toggle switch and what are all the parameters that control the toggle. And I found out like this lambda is a constant which says about the lactose and glycogen's monocarbonate transporters. So if lactogen's transporters are a little high, then the anaerobic respiration will kick in. So all these parameters I've got from the paper and I have constructed the initial condition for the model. And this is pretty much the ODE which was listed in the paper. So I've been trying to implement this, but I faced with little error while running this model. So I am trying to fix this and take a output of this. And as we planned, like maybe once I implement this model, I can go for parameter fitting and just try to extend this idea towards any of the drug applications which we can see. Yeah. So this is the update progress that I have so
So
far.
usually gamma is not an allowed variable name in antimony.
Okay.
So you have to call it gamma 1 or something else. Gamma is a reserved word.
Oh,
So in
okay.
general, that will crash.
Okay, got it.
Now, something that I'd like for the next time would be if you could explain, you showed a couple of plots in the from the papers that you were looking at.
Yeah.
I'd like it if you could explain what they mean. What is significant? What is being plotted? What does the particular shape of the curves you're seeing mean in terms of
Okay.
understanding the metabolic system? Okay.
Okay.
And we're happy to help you in terms of debugging the code as well.
Yeah, sure. Yeah, okay. So this is my first time like constructing the model apart from the basic model. So I thought like if I could study upon more, maybe I could solve this. So yeah, I'll keep you updated with my progress as well.
Right.
Yeah.
And well, that is a bit of a trap in antimony, that there are some common terms that you can't use. And I remember I said it in class, but until you run into it, it's not something you pay a lot of attention to. words
Mhm.
like time and gamma have special meanings in antimony, so you can't use them by themselves as variable names or parameter names.
Yeah.
And sometimes when antimony crashes after that, it doesn't give a best error message that's very informative.
Mm.
Okay. Anything else you wanted to present it today? Roying, thank you again for being understanding. I'm sorry I couldn't come in myself today. Would you like to show us where you are with your project?
Yeah. Sorry, I went to the classroom and I see no one's there, and I come back home, so I'm late.
I'm sorry, I sent an email, but I realized it was a little late. I was hoping to be able to come in, but then I was not feeling well, and I decided I didn't want to expose everybody to whatever virus I have, so I thought it was better to do it from home.
Okay, so I'm having a problem here, and let me share the screen. So I download the model from the link that the paper provide, and it's a SBML model, and I use the tool to translate it to the antimony model, and so I try to plot it first, and I can see the curve here. So there's two pathway here, and in the end of the pathway is the ERKPP, is the double phosphorylation, and the AKTPP is also the double phosphorylation of AKT. And then this is the one that is controlling the contact of these two cross pathway. And so I've been thinking how can I make use of the drug response data here. So we know that the drug can inhibit protein. So I'm trying to like lower the reaction rate of the MEK pathway, which is the MEK pathway. I think it's somewhere here. Yeah, this one. And I lowered it, and the peak will drop. The ERK phosphorylation rate will drop because it's protein in this pathway, and the AKT double phosphorylation is not affected. So I'm trying to understand how can I make use of this to align with the drug response. And the IC50 value, so I think it's how much the survival rate of the cell line after the like 50% will die after a certain amount of time. So I use the same cell line, which is the breast cancer cell line. And so I'm trying to I don't know how can I use this data with the model. So I just try to make the AUC curve to drop to 50%. And so maybe this is the inhibition parameter. It's like 0.3 scale. So it will drop to like 15%. Is this correct? I'm stuck here.
So this is the area under the curve. And what you're looking at is when you're inhibiting this one, the K19, then you're saying that the reaction in this one pathway is reduced, and you're measuring the degree of reduction as a function of the concentration. Well, here you're measuring it as a function of the value of K19.
K19, yeah.
And so then the question would be, if you have that chemical in the environment, what is the degree to which K19 is reduced as a function of the concentration of the drug. If you assume that it's linear, then what you've done here would be basically make sense. Sometimes that inhibition isn't linear, and then you have to worry a little bit about that. But I think to begin with, this is reasonable. As you point out, the IC50 is tricky because it's not necessarily a linear result. In other words, the fact that half of your cells or half of your cultures survive doesn't really tell you what the rate of a particular process is. And so you'd have to make some hypothesis about what the if you knew what the threshold in this plot was for cell death, then you could perhaps compare that to the IC50 level a little bit more. Pedro, I mean, this is not so far from the things that you've been doing when you've been thinking about drug treatments. So do you have any ideas here about how to make this kind of connection?
I don't know what's the goal here.
I think the goal, well, you should say it yourself, but I think my understanding is that the goal is that you have a drug, you know the mode of action of the drug, you would like to be able to see that mode of action play out here in the output of this pathway. And fundamentally, it's a calibration question because the drug is given essentially at IC50, which is more or less a hill K, capital K. And what is it that you do with that? So here at 1 micromolar, it looks like and the way they've showed it, it looks like 1 micromolar would be the well, but this is by cell line.
Yeah.
So
yeah, this is not a concentration dependence.
Yeah, no. So there is some cell line where 1 micromolar is the IC50.
Yeah, exactly.
There's some cell lines that are quite insensitive where you need 10 to the 3, and there's one that's very sensitive where you need 10 to the -1.
Yeah, so you choose a cell line and you know the IC50 of it. But you still don't have the profile. They may have the profile somewhere to know the IC50. They need the dependence on concentration.
Right? You'd like the dependency of survival for a particular cell line as a function of concentration to see what the shape is.
Yeah.
If that's available for some cell line.
It should exist somewhere, because otherwise they wouldn't have the IC50.
That's funny. That's also not a concentration. The x-axis is a list of drugs. So I think the data sets probably exist, but you may have to do a little bit of digging to find them.
Yeah. Yeah, what I will do probably I would pick a drug and then search the drug.
Pick a drug and pick a cell type, and then ask the question: what's the dosimetry for that particular drug for that particular cell type? And once you've found one or two, you'll be able to find more. It may even be in this data set here, but I don't know where you'd have to go to look for it.
Okay, I'll try to find more detail about the drug. I think this is the drug name, right?
Yes.
Okay, I will search.
Let's try. Can you choose a certain cell type here?
I tried certain cell type here.
Cell line, yeah. Select that. Let's see.
So,
Drug target the best cell line.
Well, That's what drugs does the cell respond to? Again, it's not,
Oh.
that's for all the drugs.
It doesn't fix both the drug and cell line then.
Yeah. So you probably need to do a search. Why don't you cut and paste the drug name and the cell type name just into a Google search and see what happens.
Or just write IC50. IC50.
And I'd type the word sensitivity.
Yeah, could be too.
Well, there's a dosing label. I mean, there may actually be explicit data on how that drug binds to that particular component of the pathway. At the conference, this conference last week, I was saying that there were a lot of flux balance analysis, like the things Dylan is doing, but there were also people trying to do direct calculation of effects of particular drugs on reaction rates.
"12 nanomoles per liter is the IC50 of one of those drugs. That's very, very little.
Okay, I will try to find more detail of a drug later.
I think it's a really interesting thing to do. And so I'm looking forward to seeing it. But I also don't, I'm not, again, I'm not an expert unfortunately, I'm not an expert in the particular thing that you're working on here. And so I know that people do try to do calibrations of drug effects of the kind that you're trying to do here. The particular pathway model you have has a pretty large amount of detail. And so I would think that there should be an in vitro assay for cell survival like the one you showed that would work. So my guess is that you may not find the data you want for every cell type and every drug, but there should be, at least for representative drugs, you should be able to find it.
Okay.
Thanks, great. Well, I appreciate everyone's work. Now I want to come back to some things that in a sense are very simple. And those are coming back to some of the ideas that Pedro went over last week. And the first one came about is thinking about the concept of fitting. And we've already seen this a little bit in the discussion we just had with Roying, which is that when you have a model, typically the kind of fitting that we do is we're trying to fit model parameters, but there may be uncertainty about the model structure too. There may be pathways that we didn't include in our model or possible different kinds of feedback that we might not have written out in detail. And so given a set of a model structure, then we could ask what set of parameters give us the best agreement with some target. It's a little harder to do fits for model structure because in principle, there are an infinite number of model structures. And they also are not continuously deformable into each other. At some level, you could imagine, for a network model, you could imagine every possible link between every possible node and give most of those a weighting of 0. That would be like an all-to-all neural network. But in fact, it's not usually practical to do that. And so optimizers that look at continuous variation of parameters won't work for model structure. And a couple of weeks ago, we had a talk by James Sharp from Barcelona, who's written a very nice modeling package called Yala, a very high performance one. And he was doing exactly this kind of analysis where he said he has some particular, in this case, gene regulatory network components, but he doesn't know what the activator and inhibitor feedbacks are. And then so he models different permutations of activation and inhibition between those components. For each one, he fits that model architecture to his experimental data, and then he looks for all of the model structures that agree reasonably well with when they're fit. So first you have to pick the model structure, then you do a fit, see how well you do, and then you have to pick another model structure. That becomes quite expensive because the fits for individual model structures are already fairly expensive. And then you have to evaluate many, many possible model structures. And so this idea of a model structured input parameter is something that we really need to be aware of, because very often the diagrams that we're going to look at, whether they're gene regulatory networks, metabolic networks, or signaling networks, are only fairly rough approximations to the real complexity of the biology. And so there are a lot of missing interactions and potentially missing interactions and feedback. And we don't know a priori whether those are important or not. And in some cases, we may not even have experimental data on what the interaction networks really look like, and may only know the list of components. And in those cases, we have to do a lot of extra work. And I'm going to come back to that in the idea of a very simple misfit, where we know what the model structure is, we assume the wrong model structure, and then ask the question, could we tell that we made the wrong assumption about the model structure? The answer is sometimes yes. If you're lucky, the wrong model structure won't fit the experiment. But in some cases, winds up there are multiple model structures that could fit equally well or almost as well. And in that case, you're in trouble. In reality, what you should do in those situations is use what are called ensemble models, where you consider multiple model structures simultaneously and then look at all of them together. That is something that becomes fairly expensive. So, for example, in your case, if you think that the drug might affect K19 or K18 or K17, you might build simulations where it did each of those things independently or in some mixture. And then you might ask the question, how does the drug concentration affect the level of those parameters? Does it increase them or decrease them? And if it increases them or decreases them, you expect it to do so probably to begin with some kind of hill function, whether it's a linear one or a logarithmic one. And then you have to say, now that I've made that assumption for the hill function, I have to remember what the hill exponent is, what the hill k is, which would correspond to your IC50 probably. And then also what the rate of response is. And so you'd have to do those multiple fits. And so actually this kind of thinking about model structure comes back very much to the things that you were just discussing and grappling with in the case of your drug treatment. Coming back to a simpler set of questions, we introduced the very simple idea of the residual. quadratic residual, the chi-square. And that's typically what we'll use as a cost function. But there are times when you need logarithmic cost functions or other structures. Something that we do have to think about when we're dealing with Did I lose my Zoom?
No.
All right. Sorry about that. Interesting. Sorry, PowerPoint crashed on me. So I was talking as if I was talking about this slide, which is this difference between parametric adequacy and model structure adequacy. And I apologize for that not showing properly. I only realized gradually that PowerPoint was not actually displaying for you what it was displaying for me. And I think Pedro last week went over this idea of a parameter optimization workflow and validation. And here, there's the idea of you have experimental data in a model, you do a fit of that, you do parameter confidence estimation, which Pedro will show you how to do next week, and you get some set of models which represent an ensemble of models that are compatible with the experimental data. And those might also include different model structures, although Herbert doesn't really talk about that very much. Another thing that you talked about last week a little bit was that there are different kinds of optimizers. And now it's jumping to the slide that I was stuck on a minute ago, where you use a chi-squared optimizer, for example, where you're looking for the mean square distance between the target and the predicted values. That's a reasonable thing to do, but that's assuming that there's a single time series of data points that you're trying to match. You might want to do something else like a logarithmic value. There are a bunch of different, if you've done machine learning, there are a bunch of different cost functions that are used besides chi-squared. The other thing is that y, your output variables, could be a vector themselves. You might have 4 species and you want to match the experimental values of all 4 of those species around. And so then you have to decide how to weight the contributions to your total error of each of the species. If the amplitude of variation or the values of the different species are different, then normalization and weighting becomes very important. As an example, suppose that the value of something is almost always 0 and only occasionally non-zero. If you include all those 0 values with chi-square weighting, your system may force the value to be 0 all the time, whereas the only thing you really care about is when the value is non-zero. And so you do have to think carefully about what appropriate weights are for this kind of fit. Pedro went over some of the optimization methods. A classic gradient descent, which is used a lot in neural networks, simple neural networks, for example, assumes that the cost function and the system that you're working with are differentiable. That's great when it is, but a lot of times you can't actually do, it's especially good when you can do a symbolic differentiation, which you can do often for neural networks. But in most of the cases we're going to be working with, we don't have the ability to do symbolic differentiation. If we have discontinuous models, like different model structures, we can't evaluate a derivative at all. And so the simplex method is one of the ways that one can try to avoid actually calculating derivatives directly. In the simplex method, you pick, in this case, if you're in p dimensions, you pick a geometrical object with p+1 vertices. In the simple example in a textbook is a two-dimensional parameter space, in which case you draw a triangle. And so you have 3 sets of parameters representing the points at the edge of each corner of the triangle. And then you try to move to avoid the bad values, which is equivalent to stochastically solving. Well, actually, it's deterministic, but it's equivalent to solving gradient descent without actually evaluating the gradient. And so here, in some parameter space, which isn't drawn, we have 3 initial guesses of parameter values. We have a pair of parameters at each corner. We calculate the centroid of that, for the parameter that's in between all of those. And now we pick, of our 3 points, we find out which one gave the worst result. In this case, it was the one at the top. If that was the worst one, we reflect around the centroid and come up with a new point, which is going in the opposite direction with respect to the 2 better points, which is this P34. So effectively, we've said there's the steepest gradient is in the direction of the green line, and we're going to move, we know moving towards the original point was bad, so now we're going to try going the other direction. And if the reflected point is better, we say, well, we're going downhill, and we keep going, and we go further in the same direction. If the reflection is worse, then the best point in that direction is somewhere between our initial point and that reflected point. And so we find a point inside of our original triangle here that's a contraction. And if the contraction is still worse, then we contract our whole triangle towards the best of our 3 points. And the goal is that our triangle is going to walk around in space, exploring parameter sets, but eventually we'd like that triangle to shrink to give us a set of 3 parameter space sets that are all pretty close to each other. And to the extent that we can't get those 3 corners to converge on each other, that's giving us an estimate of the uncertainty of the parameter estimation. And that's actually a pretty quick and effective method. The problem is that it's deterministic, and so you could get stuck in local minima. And Pedro showed you this case of, in a very abstract way, these are now one-dimensional parameter fits. of some of the pathologies you can have. Ideally, here you have this nice parabola. You walk down the parabola by gradient descent to your best case. On the other hand, if there were a region where changing the parameter value didn't change your cost function, your gradient descent wouldn't work. You wouldn't know where to go. You could have local minima where you get stuck. Simplex can get stuck that way. You can have multiple local minima that are close together, in which case you don't know which one of them is the best. And you also have what are called golf course or potentials, where you have a very narrow hole, which is better than everything else in your parameter space. And if you use large steps, you can jump over it and miss it. In general, there are a couple of basic guidelines. The closer you start to the final target, the better off you are. And so if you could come up with some kind of arguments about where the octave is likely to be, that's very helpful. You'd like to limit the range of possible values you explore to make your solver run in a finite amount of time. And most importantly, you should always run the optimizer multiple times, starting from different initial conditions. Because if you have local minima, you're likely to run into different local minima if you start from a different initial state. And so if each time you run it with different initial conditions, it converges, but converges to a different value, that's telling you have something like B or D, which is fundamentally difficult to find. E, there's not a lot you could do with. You have to be patient. In high dimensional systems, these are quite tricky to do. Pedro showed you this video from YouTube of simulated annealing. Here you have a cost function represented as a 2D surface in a 3D space. The parameters are in X and Y, and Z is the cost function. And here, simulated annealing is the stochastic method. And the important thing about simulated annealing is that you calculate the cost of your current position. You propose to move to a different parameter space set, epsilon I plus 1, and you calculate the cost at the new position. And then you take the difference in cost between the current and the new position, and you apply a Boltzmann factor to that. If the cost of the new position is less than the cost of the current position, you jump to the new position. However, if the cost of the new position is higher than the cost of the current position, that is, you're going uphill, you still have some probability of jumping uphill, and that probability of jumping uphill increases as the T for temperature increases, and decreases as the cost difference increases. And what that allows you to do is it allows you to climb out of local minima and hopefully find the global minimum. The advantage of that is you don't get stuck in local minima. A disadvantage is that, one, you can climb out of global minima as well as local minima. And two, it can take a very long time for this to converge. You have what are called annealing algorithms, where you say, I start with a high temperature where I jump around and explore the space a lot. And then when I believe I'm near my target, I reduce the temperature gradually to reduce the fluctuations and hone in on that target. And that's a powerful method. It's something that we use a lot in our work, but it can be slow. It is dependent on how you pick the temperature and the annealing schedule. And it's stochastic, so every time you run it, you're going to get different results. Genetic algorithms take the concept of you pick a pair of parameters, you pick that for a whole bunch of different initial conditions. You evaluate the cost function. In this case, the cost function is very rough, very spiky, which is very hard to evaluate with a gradient method. And it also has big regions where it's very flat. So out in this green region, a gradient method won't work because moving around in there doesn't do anything. In the spiky region, a gradient won't work either because you get stuck on these high peaks or low troughs, and you can't, with, for example, simulated annealing won't get you out of there either. You'll get stuck. And so genetic algorithms, you generate a whole cloud of initial parameter values. You evaluate the cost function for each one. You pick some subset of them that are pretty good. And if it's good enough, you say you found your target. If you haven't, you reproduce your sets of parameters and mutate them. So for example, if parents are P1 and P2, the offspring is a linear combination between P1 and P2. So it's between P1 and P2. Mutation would say that you randomly change the value of one or more of the parameters in your set. And that's introducing the noise the way you do in simulated annealing. But the advantage of these kind of parameter cloud methods is that you don't get stuck on single local minima. They can handle flat regions of parameter space, and they can also handle those spiky golf course-like potentials. Again, this kind of simulation is slow. It's quite expensive. Works better on parallel computers, but it can be the only way to get reasonable solutions under certain circumstances. So again, for optimization, we have to decide what our target data are. We have to pick a model structure, multiple model structures to try to fit. We have to say what parameters we're going to change. We have to create our cost function. We have to tell the optimizer which optimizer method to use, which residual to use, what parameters to vary, importantly, what additional values we're going to use and what their allowed ranges are. And that's always the workflow for running an optimizer. And now we're going to come to the idea of a misfit. And that's the reason I introduced the idea of structural uncertainty in models. Just because the model fits the data doesn't mean that the model structure is right. And one way to test it, and this is done a lot in neural networks, is to have some reserve of target data which you did not use to fit the model, and ask the question if the model correctly predicts regions where it wasn't used, which were not used in the fit. A good model should be able to generalize over wide ranges of data, including data that, or parameter sets that are outside of the region of training. And so this is what we call cross-validation. You have a training set and then a test set. If the model fails to reproduce the test set, then you have reason to believe that you have a structural problem with your model. That's a misfit. And Herbert has a whole section on bootstrapping methods that go into some detail about one approach to doing this kind of validation. So misfits could occur in a variety of ways. If we don't fit our model to data at all, then we're lucky because we know our model structure isn't working, although it's possible that it was a convergence error in our optimizer. But if the model fits the training data, but not the same system under different conditions, that's serious. And again, there could be different kinds of model structure failure, one of which is that the actual arrows in our diagram are wrong. We have an inhibitor where we should have an activator. There's a missing connection. There's a missing node. But even if the network architecture is right, the rate equations could be wrong. We've talked about how hard it is if you have multiple signals coming in to regulate one reaction. How do we combine them? We don't have any a priori way of doing that. And so that's a place where it's easy to have the right model layout, but still have the wrong rate equations. And even if things fit for everything we have, it could still be wrong because we had not enough data to be able to determine definitively what the model structures are. And so it's always a good idea to try some additional model structures and say, do they fit the data as well as what we already did? So let's actually do an exercise with that now. So first, generate some surrogate data, and we'll just do our very, very simple A goes to B, B goes to nothing, and generate a synthetic data set for that. And now we'll say, what if instead of first order linear reaction, we had assumed that the reaction A goes to B was actually governed by Michaelis kinetics, K1A over capital K plus A goes to B, B goes to nothing. Try that out using the code you wrote last week and ask the question, does the fitting algorithm return anything? How good is the fit? And when you change initial values of A and B, once you've done the fit, does the wrong model structure do well or poorly? So what you'll need to do is first you'll generate your training data. A goes to B, B goes to nothing. Then you'll try to infer K1, capital K, and K2 for the wrong model. Once you fit the values of K1, capital K, and K2, now you're going to plot the correct A goes to B, B goes to nothing time series and the misfitted K1 over K1, A goes to B, B goes to nothing time series on top of each other for different initial values of A and B. Is that a clear exercise?
Think so.
Okay. And I don't think you did this last week, so give it a shot. And if you need code for doing this, we have notebooks which have it done out, but I'd like people to take a few minutes and try it based on the code you wrote last week. If you need help, please speak up, and also feel free to ask each other for help. And if you need one-on-one help, I created a breakout room, and I have to stay in the main room, but Pedro could go into a breakout room with people individually if you need help that you don't want to be put in front of the whole class. Okay.
Are we generating, so we're generating the data using that first one
Right,
and fitting it to, okay.
right. And I was just texting you, if, since you weren't here last week, if you want a notebook which has the basic fitting algorithms put together so you don't have to write the wrapper and everything else, we could give that to you. Or
I
maybe,
might give it a shot, but it's probably
okay,
not bad to have that.
because writing the wrapper takes a little bit of time. Once you have it, everything else is pretty easy, but it does take a little bit of time to get to write the cost function and everything else. Have you ever used the SciPy optimizers before?
Yeah.
Okay, so if you may have code to do it already.
Okay, I'll give it a shot.
Well, Lakshmi and Roying, do you have the code from last week that you were using?
I do.
Good, let's see.
Yeah, I have.
Dylan, do you have the code? The base code for fitting?
No, is it possible to just get it pasted? I think,
Okay.
okay,
I will send you the link to it.
okay, thank
You
you.
will be able to run. Right there.
Well, thank you.
I put it in just as text in the chat too.
I can do that.
No, well, I put mine in, but you may have a different a different version that might be better, different. So if you have code that you like, you could put it in that.
Yeah, it's exactly what what is on the Colab.
Okay, great. I'll give people another 5 minutes. Okay. If you need help, please reach out. If you're done, please let us know because we can give you some things to generalize.
I have got output, but I'm not sure. But it is misfitting. Can I share?
Okay. Sure. Please take a look. Let's take a look.
Okay. So this is what I got, and I have given in residual the correct model, and I have generated the data from the right model, which was there, and my initial conditions were this.
Okay. So
Sorry.
you probably need to fit both A and B.
Oh yeah, I've tried with A and I'm getting this output. Okay, I'll
Okay.
do B.
Well, so if you're going to fit A and B, then you have to decide how you combine the residuals for A and B.
Okay.
But
You should have the code from last week. I think you generated your own for 2 variables.
I used the template like code template from last week, but I've generated for this model and then I have done only for A. So okay, I'll do it for B as well. But is this right? Like it should fit, right?
Roying,
What
how
model
about
were
you? Were you able to get a fit or not?
I'm having the same issue.
Okay. Well, let me come back to something, which is, in fact, in this case, you can't fit it. If you allow K1 and the Michaelis K to change together, it's actually possible if you make K1 over K K1 and K both very large, much bigger than A, then effectively the A in the denominator disappears, and you get K1 over K1 over capital K times A, which can then be fit to K1. And so if you allow K1 and capital K both to vary without limit, you could actually get this to come pretty close to the target. But for any reasonable ranges of allowed K1 and K, it won't work. And the good news is that it's not going to work repeatedly. Lakshmi, how many different initial conditions did you try when you did when you tried to do your fit? Did you try a lot of different initial conditions?
No, only one.
So why don't you try running it again with different initial conditions? And also, what did you use for the range, the allowed range of K1, capital K, and K2?
Initially I used 1, 1, and 1.
That was the initial values, but did you constrain how big or small those three parameters could get?
No.
No. So, which optimizer did you use?
1 second.
Which optimizer did you use when you were doing the optimization?
Minimize.
Because it's also going to depend on which optimizer algorithm you use. Ying, what about you? Did you use a
I'm using one for K and V. I think
actually, if we come back to, okay, I'm confused. Did you see, I'm sorry, somehow the screen share was a little bit confused. Did you see this screen or did you see something else?
We saw that.
Okay. Because I'm seeing also Varalakshmi's code. And looks to be, Varalakshmi, that you're using differential evolution in this code. Is that right?
No. That was not my screen.
I
All
think
right.
she's using minimize with
Yeah, minimize,
Nelder
optimize dot minimize.
Mead.
Okay. So let's take a look at your code then together.
Okay, do I share?
Mm-hmm. Please. And Dylan, if you make progress on this, that would be great too. Okay, so let's look at your optimizer.
Mm-hmm.
So why don't you try one of the other optimizers for Lakshmi?
Yeah.
Not minimize, but one of the other optimizers.
Mm.
Try differential
I want to.
evolution. Yep, yeah, this one.
Okay.
Yeah, I don't know if they will ask for different
The arguments
arguments.
you have to give the range for each of the parameters.
Oh, yes, true.
Mm. How do I iter that? Like syntax for that? Hmm.
Check the documentation. I don't know if this one should it's a you have to provide a list of tuples, I think.
Okay. Mm.
So yeah, go differential evolution. No. This is SciPy, not Tellurium. The optimizer is SciPy. Differential evolution. Yeah. Right there.
Okay.
Okay, check an example.
Sample. Mm.
Yeah, it's tuple.
Okay.
Above, it's above, it's
The
bounds.
bounds, yeah.
So you can see my screen, right?
Yes.
So I give it as but with a bounds minimum value. Can we
It's a
start with
list of
0 to?
tuples. It's a list of tuples.
Oh, okay.
Yeah. I think.
Does it do?
Yes.
How many parameters do you have?
Right now I'm just passing 2.
How
Of-
can you fit if you only have 2 parameters?
Hmm,
Well, you're not fitting B, so I guess you don't need K2. So you're only fitting lower
A.
K1 and capital K?
Yeah.
What
No,
what
that too, like
what
3.
what parameters are you fitting?
I'm fitting K1 and A. So,
Why are you fitting A?
mm,
The initial condition of A.
You know what the initial value of A is then.
okay.
And if you don't fit capital K, it can't work.
Okay. Let's do that. K1 and K should be fine, right?
Well, you have to use the correct value of initial value of A. So that would have to match what you did in the other where did you generate the training data?
Yeah.
Okay, so if the value of A and B, initial value of A and B were correct, that should be all right. So try that.
Yeah. Okay. Okay. Oh, okay. Sorry, I have to do this. But in our residual, like we will not receive K. Like how do we actually do that? Because okay, sorry.
I'm sorry, I don't understand.
No, I was confused. I'm sorry. I'll just
No, don't randomly code things. Tell us what you're trying to do.
okay. So while trying to get the residuals here, so I didn't correct so this was my correct model. I didn't put the misfit model here, so I was just trying to do that.
Okay.
So
Well,
in my
if you
yeah.
had the correct model, then you should
Mhm.
definitely have been able to fit it. So maybe the first thing to do is try the correct model and check that it fits.
But with my correct model, I will not have the parameter K, so I cannot
Right.
try
So
to
then
fit that with that
so
parameter.
then you'd only have K1 and K2 to fit.
Yeah.
And if you don't match for B, then K2 won't do anything. So, but what you have there should be all right, I think.
Okay.
I'm not sure why you have the model twice. Okay, I see that's your result at the end. Okay. I think you can adjust the optimizer so it reports the intermediate values that it's considering. So you might want to do that. All right.
Mm.
So it failed. Okay.
Mhm.
So why don't you try a different initial value of the parameters?
Mm. You mean like you want me to change the optimizer or
I
the
want you to
concentration?
change the initial values of the parameters
Mhm.
K1 and capital K. that you're
Okay.
going to get passed to the optimizer.
Mm.
Is that where you do that?
Mm. Like you want me to change with the thresholds, right? Like, or inside the model. Like, I did not understand your point.
Pedro, maybe you can clarify.
What's the problem?
Uh, so I have to change the initial values of the parameters.
Mm-hmm.
So to fit that, like I have to change the thresholds here, right? Or
Yeah, it is automatically randomly picking values
mm,
So
across
then run
these
it,
ranges.
if it's picking a random initial condition because you're not specifying it, that's okay. Then run it multiple times and see if you get the same result.
yeah.
That's also differential evolution is genetic. So
So
it
try
is.
running it again. And then remember something that I said at the beginning, which was under what situation did I say that you might have this work or almost work? What was the condition on K1 and capital K relative to A0 for the misfit model to work approximately?
Oh, these are bounds. These are not initial conditions.
That's right.
Yeah.
So
So
if you're confining K, what were the values of K, what was the value of K1 that you used in your first model, in your synthetic data?
Uh, uh, K1 and I mean K1.3 and K1.
I'm sorry, I didn't understand what you just said.
So I in my synthetic data I used these parameters.
Okay, fine.
This was
So
the model that I
0.3,
used. Yeah.
fine. So if you make lowercase k1 equal to 30 and capital K, no, don't change it there.
Okay.
I need you to, I understand you want to do things quickly, but please listen
Okay,
first.
sorry.
If you make lowercase, if you make lowercase k1 in the misfit model, in the Michaelis model, equal to 30, and you make capital K1 K equal to 100, what happens? Try that.
Okay.
Now, I have a question for you. Is that going to work, what you just did? Why or why not?
Mm, it sh it should work, right?
Well, what does the optimizer do?
So optimizers will for this particular model, the optimizer will get the residual values of this with these initial conditions and then try to achieve the simulated value with this.
It won't. Look at the output, 1 and 0. What did you say the ranges were?
Oh, okay. So we have to increase this range.
Mm-hmm.
to 100.
Well, more than that, probably.
Okay. What, 0 to 500 too good?
That might be all right. I don't know. I'll tell you one thing, it's going to be slow when you do that, but
Okay.
Dylan, are you able to get this to work at least in principle at this point?
I have generated data and I'm doing residual stuff now, so
Great, great.
sort of.
But the moral of this one is actually, for this case, if you provide a reasonable set of limits for K1 and capital K, there is no result that works.
Mm.
And so you know that it doesn't work.
Mm.
Actually, that worked pretty well, huh?
Mm.
Look what it did. What did it do?
So we increase the
No, but
range.
what did it return?
Uh, it returned 152 for K1 and 500 for K.
Okay. And if you use the Michaelis function for those values,
Mhm.
how does that compare with just the constant K1 from the old one, or 0.3?
Okay.
That's a question. Hmm? Does somebody want to answer my question? Or maybe I can use a whiteboard. So I have here, can people see this? Can people see the whiteboard?
Yeah.
Okay. So in the correct version, I had K1 equals 0.3. And the rate law was K1 times A. In the new one, my rate law is K1 times, let's call it K1 prime so I can keep them separated from each other. K1 prime times A divided by capital K plus A. Okay. And now what were the values of K1 and K1 prime and K that your fit gave you very largely? What did your fit return when you ran the fit?
It did return
What
the
value of K1 did it give you, and what value of capital K did it give you?
K1, it's 153 and K, it's 500.
Okay. So now let's try this. Let's look at let's try A equal to what, and what is the initial value of A?
20.
20?
20? Yeah.
20. So our true one is 0.3 times 20, which is 6. Our not true one is 153 times 20 divided by 500 plus 20. And can somebody give me the result? And paste it into Google and you can get the result. I can't do that here in my current screen. Let me see if I can get it.
It's 5.88.
5.88. That's not too bad, huh? 6 to 5.88. What if A0 only gets smaller? What if A0 is equal to 10? 0.3 times 10, 3. 153 times 10 divided by 500 plus 10 equals what?
3.
Well, better be 3 point something, but anyway, let me say it'd be a little less than 3, actually. Not by much, but it's almost 3. So what you're seeing here is that if you allow K1 and K both to vary together and get very large, then in fact, you can replicate your result. Now, if you wanted to fit B, then you have to do that separately, but that's actually really nice result. So you've got what you want. All right. So in this case, my slide was really not right. It depended on the range. I said that you couldn't fit. And it's true that you can't fit if you apply a narrow range of parameter values. If you open up the parameter values, Verrill actually found that you could in fact fit, because if you make K1 and K both very big, basically you lose the Michaelis form of the rate law. And now you could try something a little bit different. Now try to fit to a Hill function. So in your fitting, instead of K1 times A over K1, capital K plus A, make it K1 times A cubed over K cubed plus A cubed. And now try again. Does it fit or not? Your initial results showed that it fit really well. So does it still fit when you go from an exponent of 1 to an exponent of 3? So all you have to do is add that exponent. That's the only thing you have to do there. What did you get? Hmm? How did it come out?
Mine is running right now. I don't know if I've done everything right yet.
All right. Relax me. What happened when you changed the misfit?
Mine, it didn't fit properly, so I extended the threshold of the optimizer. Now it's running.
Okay.
Okay. Sorry, I was working during the last one.
Right.
Is what you're looking for three different numbers?
Well, yeah, ideally you'd have three numbers.
Okay, I got 2, and 0.0281.
Right. And if you got it, in that case, it should not fit. You should get something that does a degree.
Looks close.
Okay, let's take a look together.
Oh wait. False alarm. Wait. Yeah, I guess I could share. That looks right-ish.
You want to show us what you got?
Yeah, is it not sharing?
I had to unshare my screen to be able to see yours. Okay.
Oh, let me
So,
reshare it.
okay. So which is the fitted values and which is the target?
Oh, I might have. Oh, all right. I think it's just setting everything at 0. The lines are the fitted or the target.
This is set. Yours is setting K1. No.
Okay, I might have done something wrong here.
Okay.
I don't know if I have the right A and B. So the lines are actual data and the red is the fitted. Or the dots, I mean.
Okay, that's not too bad. If you open up the fitting range, you should be able to do better. So, where it says optimize evolution, if you make it 0, 200, 0, 200, then you should be able to do better.
Does that take 100 times as long?
No, it'll take longer, but exactly how much longer, I'm not sure. Well, I'm not sure why it worked for Vera. Actually, there you go. Yeah, there you go. That's pretty good. Well, maybe not. Huh.
Yeah, it seems like it
What
did
did it
worse.
come up with? It came up with 6, 1, and 1.9. So it somehow missed the target. And probably that's happening because we're trying to fit B and A simultaneously. Interestingly, when Viral actually just fit A, it worked better.
Hmm.
So I want to maybe let's Viral actually, could you show us your results again? Can we come back to your model for a second?
I changed it for AQ and
Okay, and
QK.
what
Let's
happened
try
when you
next
did
one.
that?
It did not fit.
Let's see.
The closest one is around.
Let's see what you got.
Yeah, just a minute. But I've changed so many things, so yeah.
What did you change?
So I am trying with different initial values. Yeah, I mean like threshold conditions, but then this is the closest that I could fit, like it did not.
So that didn't fit. Let's go back to the one you had before. Just get rid of the cube and let's do the simple one. Because there's only one thing I really want to show you. And then I think that when how they move on, you can do some of the other exercises at home. That's fine.
I
Okay.
will just do. Yeah.
Okay, that looks good. So now I want you to try something, which is now change the initial value of A to be 100.
Okay.
And you're going to have to change the target also to be 100.
Yeah.
So up there, you're going to have to rerun that one to be 100. But I don't want you to redo the fit. I only want you to do the plot now, the final values of the final values that you came up with.
Oh, okay. You want this final values and the initial value of 100, right? Okay.
Yeah,
I have the same model here.
right, exactly.
Mm.
No, but that's the target. So keep that. That doesn't change.
Okay.
The one that you have to change is you have to plot now. You're going to have to plot the other model as well.
Oh, sorry. I don't
You'll
get
have
you.
to plot the model with the. You'll have to plot the model with the Michaelis function as well.
Okay.
There. No. No, don't change the residual.
Is this what you are expecting?
Yes, that's right. Well, you tell me. You need to be understanding what we're doing here. What I'm trying to ask the question is, you've got a simulation where for particular value parameters, you're able to match your target data. And now the
Yeah.
question is, does it generalize? And so what you need to do, well, but how do you know that?
Okay. But yeah, because we tried to fit it with the previous parameter. So if we change the initial condition, it might not generalize.
Right, but that's something you need to check.
Okay.
So you know that for A equal 20, it works with those parameters. So now start with A equals 100 and check whether it works or not. You do not refit. You use the fitted values that you already got.
Okay. But the thing is, we have been trying to take the different model and try to
That's right.
make the misfit to fit. So here,
Right.
the right model has only one parameter which we can check for the A. I mean, like we have only K1 and we do not have K here. So that's why
fine.
I'm stumbled. Yeah.
No, where is the model with the Michaelis function?
It's
Where
here.
did you define the model with the Michaelis function? There. Okay. Did you give it the same name or a different name as the model, the target model?
The same name.
Okay, that's probably not a good idea.
Mm-hmm.
You want to give it
Okay.
a different name, M2 or something like that.
Oh, okay.
But what you want to do is you want to plot the model with the Michaelis function on top of the model, the true model, but now with initial A equals 100 instead of A equals 20. So what you got there is correct. So you want to run that, you want to plot that model. So you want to run this, you want to run that.
Okay, I cannot take this model separately out because I have defined it inside a function. So
Right. So
that's
copy
why
it,
I cannot
copy it,
directly
copy it
combine it.
into another cell and run it.
Okay.
But call it M2 or something like that so that you can plot, run it and the other one together.
Okay. Okay.
Good.
The initial condition is right. And here you want me to use the fitted model, right?
Yeah, perfect.
119.73. Okay.
Okay. I plot those on top of each other. That's good.
Mm.
There you go. Yeah. You got it right, but you need show equals true for the second. Okay. Boy, that coding assistant's pretty good. Okay, there you go. So it's not terrible, but it's not as good as it was. What if
Hmm.
we make it, what if we make A0, the initial value of A equal to 300? Getting worse, huh?
Hmm.
Now make the initial value of A 1,000. So in this case, if the initial value of A is close to the one that we use for our optimizer, our misfit works fine. If we move
Mm.
away from the value of A that we used in our optimizer, then the misfit gives us something that's wrong. And so this is an example where we're able to fit it for a specific set of data, but it doesn't generalize. So that was really helpful. Thank you very much. And thank you for being such a good sport about walking through that. I really appreciate it.
Thank you.
Okay. Dylan, how are you doing in getting it to work or not work? And Ro Ying, and how about you?
Medium, I guess.
Okay, let's see what you got.
Sorry, I was blocked. Am I doing this right of fitting the parameters? I think you're muted.
You should be fitting K1,
Yeah.
capital K. And what's V? What's capital V?
Yep, that's might be part of the issue. Okay. Yeah. So. Okay.
The other thing is that in this case, we know that the B for K2, we know that the K2, the model is correct, although we wouldn't know this a priori. And so we could constrain the value of K2 to be close to the one which we know is correct.
Oh, and then just make it kind of go faster.
Yeah. What was the actual value of K2? I think it was 0.1, wasn't it? 0.4. So if you constrain K2 to be between 0 and 1, it'll speed things up a lot. Like, oh, and you're using the cubic here?
Yeah, did we switch?
Well, I'd make sure that it works without the exponent first before you try the cubic one. It's a little bit simpler if you don't have it. Roying, how did it go for you?
I'm still working on the first one. It takes a very long time for the differential evolution to fit.
Lakshmi, maybe you could share your code because your code seemed to converge at about 30 seconds.
Yeah.
Um, so I've tried to like using a very large range, and Colab just stopped me from doing that, and I have to scan it like in a very small range because I
So
have 3 parameters. So she used only 2 parameters.
right. So maybe, I mean, you've made a good observation, which is the more parameters you try to fit at once, the harder it is to have it converge. And so my initial thought when I saw her just fit the value of A was that it wasn't a great idea, but in fact, maybe trying to fit just A and not trying to fit um, A and B together was a good idea. Now this looks pretty good, huh? Let's see.
Don't
Are you
think
sure? It looks
so.
like you're fitting. Are you fitting B to A?
I don't think so because B's going up and then following the A.
Yeah, it looks like you're trying to force B to match A. So it looks like somehow your residual isn't calculated right. So if I ever do this again, I'm going to have people just fit A to begin with, the way Vera Lakshmi did it, and see if that works better.
Just
So here you just appended B and A to each other and then calculated the residual. So A and B are weighted equally. What if you don't do B? So what if you comment out the diff append B lines and at the top up there too? And then you'll have to not fit M dot K2. You try to fit M dot K2 at no. Try that. Inspected 3 got 2. So somewhere we still are, okay. Convergence error.
Don't know what that means.
Let's see, what's the range over which you're doing the simulation of time? Simulate
10.
0 to 10 to 100. That looks all right. That looks all right. So I think what's happening, well, let's see. Okay, so it's failing during a simulate, but we don't know when it's failing.
At different time. Too much
Right.
accuracy requested.
All right.
Gotta go let my dog out really quick.
Okay, no worries. Ro Ying, do you want to show us what you've got while he's doing that?
Okay. So
I want to walk in a second.
this is the first one without a cubic.
Yeah.
And
That
so-
came out really well. That looks fine.
but it's different from her result, right?
Well, so the answer is that any value where K1 is equal to 3 times, sorry, K1 is equal to 3 times capital K, and they're both multiplied by a large number is about equally good. So if you multiplied both K1 and capital K by 2, it wouldn't change anything. The fit would be equally good.
But this one is the large K. It's 200, and this is the
Okay, so then I'm backwards. So, but all that matters is the ratio between those two numbers. That ratio has to be the same as the K1 in your original one. And K2 should be whatever the value was in your original one. So this is fine. So this works. Now, Now, what would happen here is if you make the initial value of A big compared to 200, then it will fail. But again, you don't want to refit it. You want to use the fitted values and check whether they work. So now what you want to do is let's look at what you're plotting here. After you've done your fit, how are you generating that second plot?
Using Pedro's code.
So you do the optimize, and then simulate with optimized parameters. Fine. So what you'd want to do here is basically copy. You'd want to rerun it with plotting the target and the values with the optimized parameters, but so you can change the initial value of A, which you can't do here. Because here your plot is inside of your optimizer. So Lakshmi, do you have the code you use to plot your results on top of each other?
I have, okay, I can give that.
Maybe put that in the chat.
I have pasted that already in the chat.
Okay. So
with
you
my
got it.
fit.
Great. Okay, so why don't you create a new cell in your notebook and grab Veralakshmi's code and put it into a new cell at the bottom underneath those two. Okay.
This one is what Pedro gave
No, but you
last
don't
week.
want, no. This isn't. No, this isn't what. So I guess I'm not being clear. What you want to do, you don't want to be doing a fit here. What you want to do is you want to plot the target just the way you did above. And then you want to plot the misfit function with the parameter values that you've just gotten from the optimizer. So there's no fit. Get rid of def fit. Get rid of solution. Get rid of print solution.
I think we're still seeing writing's screen.
Yes, that's what I want.
Okay, I just making sure.
So get rid of line 1 there. You're not doing a fit. You're not doing a fit. So this isn't the code that I asked to share.
It's in the chat, the one which we.
Yeah. Okay. At the end, yes. Look at the code that Veralakshmi just pasted in. No, but you're not doing any residuals or anything else. You're just plotting the functions. Okay, and now you need to load the misfit function. I think this is so simple that maybe it's confusing. please grab the code that Verilakshmi put in the chat and paste it into a cell.
This is her code.
Um, that's not what I see.
Uh, did you change the model with the parameters that don't like the trained one and
Look at the code I just pasted in the chat. There you go.
I changed the A.
So now run that. Okay. But now put in the parameter values for the first model, put in the parameter values from your fit. Okay. Okay. Well, that's fine. Not bad. All right. So those are basically indistinguishable from each other. Looks like.
Yeah.
Let's see. We got R1, R2. Okay. So now change the initial values of A from 10 to 100. You see they're beginning to diverge. Now make it 1,000. Now they don't agree. So it works okay as long as the initial value of A is close to the initial value of A that you used for the fit. But for values of A that are much bigger than the initial the A for the fit, it doesn't work.
Yeah.
So that's the result we were trying to get.
Okay.
And Verilakshmi, if you could share your notebook back to people, I think that would be great. Dylan,
yeah,
are you
sure.
back?
Yeah, sorry. I just ran Lakshmi's code too,
Yeah.
and I got the same convergence issue. So I don't know. I don't know where that is coming from.
You want to screen share it?
Yeah.
I don't want to take too much more time on this, but I'm not sure why it's crashing on you. And it's failing in the same way. It's failing with that convergence error.
Yeah. Different time, but like the same stuff is coming up.
So why don't we try reducing the range, allowed range of K1 and capital K. So instead of make it 0. See if that works.
Lasting longer. Oh.
With the same problem. Okay,
Some
no,
lives.
it did converge. This is an error because of this is an error. This is a syntax error.
Yeah. Okay.
So the problem was it got into a region of parameter space where your model didn't converge.
Okay,
Probably
so
because
have
capital K went to 0. But now that's all right. So now we need to find out where the syntax error is. Line 18. Well, it's inside of the fit, which is unfortunate. But it did return a value. See, it returned 20, 100, and 20 and 100. You see, look in that.
Yeah.
So it did return something. And so the problem was probably in the plot.
Shoot, it's gonna run it for that.
Yeah, so the plot, for some reason, the plot, and when you're calling the plot, there's an error in the plot.
Yeah. All right. This is just a. I don't know why. I think my T.
And so, I mean, you don't have to do I'm not sure, you don't have to put the plot inside the fit function. You can do the plot after the fit.
That would make a lot of sense. Yeah. All right. Oh yeah, I think that's the issue though.
I mean, the reason we have the plot inside, I put the plot inside the fit originally, was that way you could see how the model was updating itself so that you could see whether you were converging or not, but you don't need to do that.
Yeah, I think I have something wrong with the time. That's just. I'll have to go through the notebook and see what's going wrong because that gave the same error too when I just changed the time. So I think I'm just doing something wrong with that.
Well, sometimes it's a pain to try to debug on the spur of the moment. And I'm sorry about that. I don't like to leave people hanging, but I would like to at least introduce the next thing we're going to do. We're not going to get through it. We're probably not going to get through it today. But let's see. Yeah, well, we're almost out of time, aren't we? Let me just introduce the thing that I guess we'll do next week, which is, am I right? Boy, I don't want to say that because it sounds condescending, but I had no idea we got through 2.5 hours already.
Yeah.
It's fine. I'm not complaining. But I would ask you to try going at home. You could look at the examples online. I realize that there's actually a mistake in my slides, and I should have shown the results that Vera Lakshmi had. So I think I'll probably replace my notebook with Vera Lakshmi's because she was able to get it to work very nicely. And she had to run off. So I think probably we should end for today here. And I appreciate people's patience. Sometimes trying to do heavy coding in class works and sometimes it doesn't. But I think seeing what people are doing and trying to help each other is not a bad thing. And I think that again, you were a little bit, it was a little unfair to you because you hadn't worked with it last week. And so you didn't have debugged code to work with from last week. And so
Yeah, I think if I just go through these things and really try to understand what the functions are doing, I should be
Yeah.
okay.
Okay. Okay. Yeah, it's a little bit that callback for the fitting function is a little bit complicated. And so especially the way it was done here, where it was done in steps. You know, as it runs it forward for a short amount of time, then it runs it forward for another amount of time, that runs forward for another amount of time. And again, that was done to make the plotting work more than anything else. But it makes the code a little bit more complicated than it needs to be.
Luckily,
All
you
right.
can AI
Very good.
these things and get a good explanation, so I should be able to figure it out.
So probably, and I realized the homework I set out was probably a lot. So I don't know if people were able to do any of it.
Yeah, is it if there's something like on the homework, I hit the like 6 hour mark and was not anywhere done with it. Is it okay to just turn it in like that for when
Yeah,
it's at the okay.
that's all right. And then also the flip side of it is if we don't get through things in class as much as we expect, then the homework from the week before I said carry it over. And so we may wind up doing that again this week. Pedro and I will talk about it and come up with a strategy for next week.
Okay.
Okay. Okay, well, thank you, Dylan, and thank you, Roying, for being willing to screen share and explore a bit. Pedro, if you could stay on for just a second, I'd appreciate it.
All right.
Sure,
Thanks,
yep.
Professor.
I want to thank you for being, I hope you feel better and I hope I feel better. And so thank you, everybody. Good night.
All right. Good night, guys.
Good night.
No.
And,
Yeah, I wasn't expecting to take that long to do the fitting.